Okay, hello everyone, it's Salar and we are in part 62 of our tutorial writing a real-time operating system. As I said in previous part, in this part I want to implement memPool. Okay, this part is for memPool implementation. Like other entities in our real-time operating system, like thread, semaphore, and mutex, you need a control block for your memPool. Let's inspect the members of this block, this structure. Like mutex, semaphore, thread, you need an ID. Okay, this is an address that point to the address of control block. Okay, memPool control block. You need a name like before, and you need some other members, for example block size, max block count, first block address, block array index, and memPool waitlist. Okay, let's talk about other members. Assume this is your memPool. Okay, assume this is your memPool. As I said, each memPool has some blocks and each block has a size. Size of each block is block size. Okay, block size. This member refers to size of each block. The maximum count of blocks. Has been saved in this member. For example, here is 4 blocks. Okay, the maximum block count of this mempool is 4 blocks. Block 0, block 1, block 2, and block 3. First, block address. As the name implies, address of first block, address of block 0 here. Okay, first block address. Block array. What is block array? Block array here is an array of integer numbers that each cell in this array point to one of these blocks. When this value is 0, this means the block is unlocked, the block is free, the block unallocated. When the value is 1, this means the block has been locked, the block allocated, and this value is 1. Okay, this is an integer array and each member of this array points to one of these blocks and shows this block is free or allocated. Block array index. Block array index. Index of last allocated block. After block creation, all of blocks are free. Okay, and block index array point to L0. Okay, but assume 2 blocks, for example block 0 and block 1 has been allocated, and these 2 value is 1 and these 2 values are 0. Now the block array index at this time point to this cell, block array index, index of last allocated block. Okay, block array index is index of last allocated block. And when operating system wants to allocate a block, the operating system must search all blocks to find first unallocated block after last allocated block. After last allocated block. At this time, if the operating system wants to allocate a block, first free block after last allocated block is this block, block number 2. It must allocate block number 2 to the code, to the color thread, and change this value to 1 and change the lock array index to this cell. Okay, and last member in this structure, memPool wait list, completely like mutex wait list and semaphore wait list. As you can see here in RTOS.h, when you want to allocate a block, you must use this function memPool allocate, and you have a timeout. If there was no free block in memPool, the operating system put the thread in memPool waitlist, as much as this value, timeout, and the thread must wait for another thread to free a block, okay, to free a block, or after timeout, the operating system will return the thread to the ready list, and the return value of this function will be null. Okay, will be null. When the return value of this function is null, this means the allocation was unsuccessful. Okay, and you can see in my repository, I've updated my repository, and in this commit memPool addition, I've implemented memPool to our real-time operating system, and this is initial version of memPool. So let's back to this slide. So ID, name, block size, size of each block, count of all of blocks, first block address, as the name implies, address of first block, block array, which cell point to one of these blocks, block array index, index of last allocated block, and memPool waitlist. This is memPool control block. You can see memPool control block here. Okay, here is memPool control block. And for memPool, we have these system calls. memPool get name is a simple system call, like other get names, like for example semaphore get name or mutex get name. memPool create new. Create one of these mempools. Create, allocate all of these blocks in memory, allocate this lock array, and initialize other members. Okay, and the next and delete system call, delete the mempool. Okay, these two system calls is like before and are simple system calls. You can see these system calls here. For example, create new. Okay, user space system call for create new and kernel space system call for create new. Read and inspect these system calls, get name, create and delete by yourself. But let's talk about about mempool allocate. Okay, what does the system call do? The main job in the system call is this part of code. Okay, but what does this part of code do? What does it do? This is an for loop. Okay, and this for loop will repeat maximum until to this number, maximum block count. For example, here 4 times, maximum 4 times the operating system do this system call, do this code to find first free block. Okay, first free block after lock array index, first free block after lock array index, maximum 4 times. Okay, size of mempool. First, read lock array index from mempool control block. Okay, read this value. If the lock array in this index last allocated block is unlocked, allocate that block, change this value to locked. If the value is 0, change this value to 1. This means the block has been allocated, and after that, by using of these two lines, acquire the address of block. First, acquire block offset. What is block offset? For example, offset of each block from this address. For example, offset of block 0 is 0. Offset of block 1, if I assume block size is 16 bytes, is 16. Offset of block 2 is 2 multiplied by 16, 32. Offset of block 3, for example, is 48. Okay? First, acquire the block offset, lock array index times to block size. Okay? After that, add first block address by block offset to acquire the address of block in memory. Okay? For example, when it wants to allocate block 2, add this address, first block address, add by 32 to acquire the address of this block. Okay, and return this value and break the for loop. But if this value is locked, this value is not 0, is 1, increase the value of lock array index by using of this line. Okay, increase the value of index. For example, when 2 block has been allocated in your mempool, the lock array index point to 1. Okay, the value of lock array index is 1. Okay, by running this code, first read this value is 1, but the value of array at this index is 1, is locked. Okay, is not unlocked. Okay, so because this value is 1, the lock array index here is 1, another time is 1, this value is locked, is not unlocked. Increase the value of lock array index to 2. Okay, another time go to the first stop for loop. Now this value is 2. Okay, lock array index in this cell equal to 0. equal to 0. It's unlocked. Lock this value, change this value to 1, and allocate address of block number 2 to your code, to your color, okay, to the color. But you must implement this part of code as an atomic part, because this code may be broken by an interrupt. Okay, you must implement this part as an atomic part. I've implemented this part in memPool allocate. This is user space system call, and this is kernel space system call. This for loop implemented as atomic part, as an atomic part. Okay, kernel atomic write, kernel atomic read. Okay, inspect this atomic part by yourself. I don't inspect this atomic part. It's your, for example, homework. Okay, inspect that by yourself. You have a lot of information about atomic part, atomic codes from previous parts. Okay, inspect this code by yourself. Okay, so the operating system allocates memory by using of this code. Okay, by using of this code for you must implement, and this code must implement it as an atomic part. Okay, so for memPool allocate, try to acquire a free block by using of this code. Okay, when free block is not available, put color thread as much as the timeout, in waitlist, as much as this timeout to the waitlist, like semaphore and matrix. Put to this list, memPool waitlist, like semaphore and matrix. The concept is completely similar to semaphore and matrix. Okay, and wait for a free block. Wait for a free block. And for memPool free, what does this system call do? For memPool free, okay, you must free a block. This is the address of a block, for example, block 2. For example, address of block 2. Okay, you want to free this block. You must give this address and ID of the memPool to the operating system, to this system call. Okay, now what does operating system do to free a block? Check if there are no other threads in waitlist. Okay, I said in this slide, when free block is not available, put color thread as much as timeout in waitlist. Check if there are no other thread in waitlist, just unlock the block. Unlock the block, what this sentence means, unlock the block, just change this value to 0. Change these values to 0 to unlock. In memPool free system call, kernel space system call. Okay, check the waitlist size. If the value is greater than 0, this means at least one thread waited for a free block in waitlist. But if this value is 0, just unlock the block. Okay, just unlock the block. Otherwise, if a thread waited for a free block, hand over the block address, hand over the block address. Assume you want to free block number 2. Okay, all of these blocks are 1. You want free block number 2. You want to change this value to 0, but a thread waited for a block. You must not change this value to 1 if a thread waited. You must hand over address of this block, this address, to the waited thread. Hand over this address. Hand over the address. Hand over the block address to most prior thread in waitlist. If the size of waitlist is greater than 0, this means that at least one thread waited for a free block. Get max from waitlist, get most prior thread. Hand over the block address to the wait thread. Hand over the block to the wait thread by using of this member. This is a new member in thread control block. Here thread control block and memPool here. This memPool block released by free. Okay, address of a block that released by free system call. Address of block that released by free system call. Put this value in this member and hand over this address to the wait thread. Delete thread from waitlist and add it to ready list and change this value returned by free. It's a member like returned by release. Okay, change this value to set to 1 like semaphore and matrix. I've talked about returned by release in semaphore and matrix. This member has a responsibility like returned by release. Here is returned by free. Has a responsibility like returned by release. You have used this member in matrix and semaphore, but in memPool you must use these two members to hand over a block address to a wait thread. So put the block address to this member and set this value. Now here in memPool allocate, if released by free has been set, you can put this value memPool block released by free address of block to return value. This is the address of block. Okay, you have put, the operating system has put address of block here. Okay, address of block here. This is the address of block. memPool block released by free. You must use this value as a return value of this system called memPool allocate. Now, before elapsing the timeout, another thread free a block and operating system hand over block to this thread, okay, to memPool caller that's waited for a memPool block. Okay, otherwise, if until elapsing this timeout, no other threads free a block, return value of this system call will be null. Okay, return value of the system call will be null. Okay, and the waitlist handler must return the thread to the ready list from waitlist, like matrix. I've completely described this part of code in waitlist handler. If until to the elapsing the timeout, no other thread free a block, return thread from waitlist to the ready list, delete thread from waitlist and insert it to ready list, and return value of mempool allocate will be null. Okay, return value will be null. Okay, so sorry, this was the implementation of mempool. Now let's see an example here in main.c. In my example, I have a thread. The priority of the thread is priority normal and the stack size is 256. And I've created a mempool by using of the system call. Size of each block is 16 bytes and we have 4 blocks in this mempool. And in thread function 1, I want to allocate 4 blocks. Okay, I want to allocate 4 blocks. Okay, now I'm in debug mode and let's to run code until here. And let's to run all of this mempool allocate system calls. You can see the return value of the return value of first allocation is here. The address of first block 1218. For next allocation is 1228. Address of next block. Okay, when you add this hexadecimal number by 16, you will acquire this value 1228, after that 1238, and after that 1248. I've allocated 4 blocks by using of mempool. Size of each block is 16. But let's see another example. First, stop this debug session and let's see another example. Okay, another time we are in debug session, but at this example we have 2 threads, thread 1 and thread 2. The priority of thread 1 is normal and priority of thread 2 is lower than priority, lower than thread 1. Okay, another time we have a mempool, but at this time the maximum block count is 3. But like before, the size of each block is 16 bytes. Okay, another time another time in thread function 1, I want to allocate 4 blocks to each of these pointers. But as you can see, at this time we have 3 blocks. Okay, but I want to allocate 4 blocks, and in thread function 2 I want to free one of these blocks. Let's debug the example. If I run the code, operating system will put to this line. Let's run my code until here. Okay, now address of first allocated block is 1470. Okay, the next block is 1480. Address of third block is 1490. 3 block has been allocated. The mempool is full. I want to acquire another block. If run another time, mempool allocate, the operating system jump to thread function 2 with lower priority. Because the mempool is full, and the operating system put thread 1 to the wait list for 100 milliseconds. Remember address of PTR0, 1470. Okay, 1470. Now I want to free block 0, PTR0, address of 1470, and thread function 2, because of this system call, waited for a block. If I run mempool free, the operating system hand over this address 1470 to this pointer. If I run mempool free, immediately the operating system another time jump to thread function 1, because thread function 1 has higher priority, and thread 1 return to waitlist by mempool free, and the value of pointer 3 is 1470. Okay, this address. Okay, so when a thread waited for a block, the operating system hand over this address to waited thread. Okay, so you can call malloc and free from interrupt. mempool alloc and free from interrupt. Okay, but try allocation and free from interrupt by yourself. Okay, and you can inspect the code here. I've completely implemented mempool allocate from interrupt and mempool free from interrupt. Okay, you can inspect the code. The code is completely like mempool allocate from thread mode. Okay, it's completely like from thread mode. Okay, this was the implementation of mempool, an alternative for malloc and free that implemented by Newton. Okay, so thank you very much to see me, and see you soon in the next part. Thank you very much.